Hey everyone, welcome back to the channel. I'm Nehemiah. In this video, I'll teach you everything I know about scalability. Scalability simply refers to how a system handles increased load. This video is the third video where I'm teaching you everything you need to know about system design. Make sure you watch the previous two before watching this one. It will do you very good. In this video, I'll have several sections talking about several topics that will help you to understand scalability. See you in the next section. One of the ways you can handle increased load on your servers is by doing vertical scaling. So I'll assume this is your client or a number of clients. So this will represent your clients. And then your clients are sending a number of requests to your server. But after some time, the requests become so many because your application solves a real problem and many people really love it. So your server gets overwhelmed, and because it's overwhelmed, the responses start becoming slow, and if not mitigated, it can actually crash and go down. So what happens? You start increasing the resources of the server. You know that your server can have resources like CPU, it can have resources like memory, or what you can call RAM. A server has also a resource that I can call disk or storage, your hard disk, and all these can be increased or scaled up. So for example, you can say, I want to increase the RAM. If your server has about maybe 32 gigabytes, you can increase from 32 probably to, let's say, 64 GB. Then your disk space can be increased. Probably if you had only a terabyte, then you increase from 1 terabyte to probably 2 terabytes. Now, this is vertical scaling. But the challenge with vertical scaling is that time comes when you hit the limit. A machine can only take up to a maximum it was built for. For example, you may find that this server cannot exceed 64 GB. So what happens when your requests are too many that 64 GB is not enough? What happens when 2 terabytes is not enough? You cannot build this anymore. You cannot increase the scale of this application. Not the application, but the server. So you hit a wall, and this is the limitation of vertical scaling. In the next section, I'm going to show you an alternative of how you can scale, which is a little bit better and can help you mitigate the challenge of hitting the resource limits of your server. Let's talk about horizontal scaling. Now, with vertical scaling, we discovered that even if you got a very, very powerful server, high-end, the most expensive in the world, with the maximum possible resources it can have, you can still hit a ceiling for all the resources on that server. Even you can hit a ceiling financially, you get. So the best thing to do would be to have maybe a little cheaper machines. And let us say this is server 1, okay? Server 1. It has some CPU, it has some RAM, it has some disk. Then again, you get relatively cheaper machine, not so expensive. I'll call it server 2. Then after that, have another one, server 3. So ideally, you have as many as you need according to your needs. So this time, when client makes a request, it's best to say clients instead of client, and there are hundreds, thousands, or millions of requests. This time, instead of all requests going to server 1, you can distribute them to server 2, and then other requests go to server 3. The whole idea of horizontal scaling is not having only one machine. Horizontal scaling is all about creating identical several servers, and these several servers have the same application code, and they are supposed to give your clients the same response. So when a client makes a request to server 3, they should get the same response from server 2 and should get the same response from server 1. Ideally, the client actually knows that I am only making a request for a resource. They don't know the server that is going to respond to them. But for you who knows that your application has become very successful and you have so many requests, you try to ensure that not a single server is taken down. So you avail a number of servers that can provide the same responses for the requests to your clients. That is what horizontal scaling is all about. More to this in the coming sections. See you as we deal with something else in the next section. Now that we agree that horizontal scaling is a little bit better than vertical scaling, let's talk about load balancing again. If you have your machines, I'll pick different color. You have server here, server 1, and then server 2, and then server 3, and then you have your clients. I'll call this client C1, client 1, that is C. Then you have another client, C2, another client, C3. And of course, in the real world, you could have thousands of clients. Because now we have this number of servers, we now introduce a black box. And this black box will be responsible for accepting requests from our clients. And these requests are then passed on to the servers. Of course, in the real world, when you need this setup, you need to have, of course, a number of servers, sometimes even hundreds, thousands, or tens of thousands, depending on your setup and the need. This black box is called a load balancer. I'll call it LB, and it will decide to which server it should send the request in your horizontal scaling approach. And of course, these servers will all have their IP addresses, which are private. So a private IP for server 1, private IP for this server, and another private IP for server 3. And of course, the load balancer should have a public IP, and the public IP is what is exposed outside to the clients. So take note of this. I touched on load balancing in a previous video, either a first video in this section, and I talked about how a load balancer decides which server it should send a request to by looking at load balancing strategies. I don't want to waste time for those who have been following this playlist. Please check the link in the description to find out the playlist and watch that particular section in the first video or second video. Please, it's very important. Let's go to the next section, talk about shared session state. So let's talk about shared session state. Let's say you have a single server, and this server is responsible for storing sessions for your users, maybe to help you to track that a user has been logged in successfully. And for every user, it happens that all the sessions are stored on this single server. But what happens when you horizontally scale? You can decide to put sessions in every server. Let's say this server has session state, this other server has session state. I want to use something that is more visible color. You have session state here, you have session state here, all helping you to track the user session. Now, if a user tries maybe to log in and is being handled by server 3 the first time, their state will be stored on server 3. The next time they try to log in or to access the site, you may find that the load balancer serves them via server 1. That means server 1 does not know about the session state in server 3. So this forces the client to be logged in again, or the user to be logged in again. The same thing happens if we go to server 2, and the load balancer serves the user's request via server 2. Do you know what happens? They have to log in again. I hope you see the issue with this. A solution could be to store the state in a centralized location. For example, you can say you can have a disk, some secure disk over here, and this disk space is responsible for storing the session state, so that all the servers that you have must access the session state from this centralized disk. This is very good, because in the real world, you may find that you have hundreds of servers and you don't want to have every server with its own unique state. It gives the users a very bad experience. What your servers need to have is only the application code. It has to be identical. Your code, maybe of Python or the JavaScript, Java, Rust, Go, has to be identical for server 1, server 2, and server 3. But remove the session state from those servers and have that session state in a centralized state. But then this is also not so good. It introduces another problem. What if this goes down? This introduces a single point of failure. As we advance in system design and architecture, we are going to introduce single points of failures, what is called SOP, a single point of failure. Now, in the next section, I'm going to talk about a solution to solve this situation of a single point of failure, whereby our session state is only on one disk. Our servers have access to that disk, but in case that disk goes down, we are in trouble. See you over there. RAID is an abbreviation. I want to define it right now. Copy, drag this, and maybe just drag it down here. So it stands for redundant array of independent disks. As simple as that. And I'm going to explain what it actually means or does. Assuming you have disks. I have disk 1 and I have disk 2. Two separate physical hard disks. With RAID, these two hard disks can logically be seen as one hard disk. They can be logically combined or used as one hard disk. In simple terms, that's what RAID is all about. But you need to know more about it to understand how RAID solves the problem I mentioned in the previous section, that using a single disk for session state actually introduces a problem. And that problem is that we have a single point of failure. How does RAID help with this? To understand how RAID can help, I have to tell you about the several types of RAID. We have RAID 0, we have RAID 1, we have RAID, I think, 5, we have RAID 6, and RAID 10. I will explain these, but I think they're actually more. But these are much more simpler and easier to explain. Now, how does RAID 0 work? With RAID 0, you have two identical hard disks, hard disk 1 and hard disk 2. And what happens is that when you get data in your system, this data goes through what we can call, or what is called, stripe data, meaning a piece of the data that is coming is written to disk 1, another piece is written to disk 2, and this goes on and on. So drive 1, drive 2, drive 1, drive 2, until all the data is written successfully to these two disks. This is very good because it improves performance. And how does it improve performance? Because instead of writing to one disk, you have the write speed being doubled, or rather, the write operation being doubled. With RAID 1, you have the same thing, two disks, disk 1. Maybe I can use a different color for explaining RAID 1. So you have the first disk, then the second disk. But this time, instead of chunks of your data being split and being written to the two disks at a time, you have what is called mirroring. You have an exact image or mirror of your data from one disk to another. So if maybe like disk 1 has the word hello, disk 2 will also have the exact same copy, hello, and not the word hello being split and being divided on the two disks. Another thing you have to know is that in the event maybe like disk 2 maybe died for some reason, you can run to the store, buy a new disk, and RAID makes sure that this word hello is duplicated on this disk again. Of course, with this, you have some performance overhead a little bit because you have to maybe duplicate everything on one disk to the other. But it gives you more redundancy. That's the good thing about it. With RAID 10, it gives you both of what you get with RAID 0 and RAID 1. What do I mean? You actually have 4 disks. Okay? You have 4 disks. I will create my simple 4 disks. Disk 1, disk 2, disk 3, and disk 4. What does it mean? You now have both striping and you also have mirroring. Okay, that's the advantage you get. But know that this means it is twice as expensive because you're getting two benefits from two worlds. RAID 5 and RAID 6 are kind of middle grounds. Let me explain. With RAID 5, this is what happens. You have disks, okay? I'll pick a different color. You have your disks. But remember, with RAID 1, your disks have mirrors, okay? What is in disk 1 is also in disk 2. But with RAID 5, you can have, for example, your 5 disks, okay? Your 5 disks. And let me say this is disk 3, 4, and 5. But now this time round, disk 1, 2, 3, and 4 are where you have your data being written to. Then you can say disk 5 is the only one that's going to help you with redundancy. So in this case, you have 1/5, okay, for redundancy. But in RAID, you have actually a half for redundancy. So having a fifth, okay, is much lesser than having half of your setup for redundancy. And something else you need to know is that in case something happened and your disk died, with RAID 5, all you need to do is to run to your store, buy, and you can replace one. RAID 6 has a similar setup to redundancy. The advantage with RAID 6 is that with it you can replace two new ones. Okay, RAID 5 you can replace only one disk. In RAID 6 you can replace two. That's the advantage over RAID 5 that RAID 6 has. This can help you with managing data and making sure that you don't lose your data using redundancy given to us by the RAID technology. I would encourage you to even read more about this. Let's go to the next section. I need to talk about session state again. I know there are more advanced things I can talk about later as I advance in this playlist, but there is something on session state I needed to talk about. That is, when I said disk in the previous sections, you can actually store your session state in a cache in a tool like Redis. So ideally, you can have, for example, your database having your data. Maybe this is a Postgres DB that is storing your session state like cookies, okay? And then you can also decide not to use a database and use an in-memory cache like Redis. And right now, if you asked me, I think I would go with Redis. Why? Because it works in memory and it's extremely fast. All I wanted to tell you is that you can have your state in a database or in memory. And remember, this database is external. It's not sitting in any of your servers. Neither is this in-memory cache sitting on any of your servers. And it's an external in-memory tool. This is the bit I wanted to tell you about session state, that you can keep your state in an external database or an external cache or in-memory tool like Redis. I want to get away with something I haven't talked about when dealing with load balancing, but you can use either software or hardware for load balancing. I know a number, but I'll talk about what is common to me. I know of HA proxy load balancing as a software. I know Nginx. I hope I've spelled this correctly. Nginx. Then we have ELB, the Elastic Load Balancer, I think by AWS. Then what else? I don't remember anything else. Can go and talk about now the hardware. For hardware, I think I remember one by Cisco. Yeah, Cisco has a tool. Then there's one I think calls it Barracuda. Then is it, let me scroll this. Citrix. Generally, the hardware are more expensive than the software. And personally, I've only gotten the chance to use only software load balancers, so I won't lie. If you have a chance using any of these, please, like Cisco, Citrix, please let me know in the comment section. Session affinity or sticky sessions is a load balancing technique which ensures that a client always receives responses to their requests from a particular server. How does this happen? It's actually very simple. You have your load balancer, LB, which sends a cookie to your client. So you have your load balancer that sends a cookie to your client. And this is one of the ways you can implement it. And this cookie can be a random number, that tells the load balancer that this random number or this number or this identifier maps to a particular server. And on every other request that the client sends, they have to send that request, including the cookie. But to let you know that a sticky session or session affinity simply means that on the initial request, a load balancer sends a cookie to the client. And this cookie is responsible for identifying the server that sent that request. And going forward, on every other request, the client sends back the request to the load balancer, and the load balancer knows to which server to send that request. The only drawback of this is that when several clients start sending requests to one node, it could overwhelm that node. And of course, there are better mechanisms that can be implemented, like I've talked about caching. But what could be better than this is called distributed caching. And we shall talk about it in a feature section in this video or another video. But I hope you've understood what sticky sessions means or session affinity. Hey everyone, welcome to this section where we're going to understand data replication. In our current setup, we have a load balancer and we have horizontally scaled. That is very good, but after some time, when your application now becomes even more successful and you have more requests, horizontal scaling isn't enough. Time comes and your application or the experience for the users or the clients becomes slower and slower. It is because of the database. You have only one database. Let me try to draw that. You have one database, and that database receives requests from all your servers. Okay, so I'll say DB for the database. So server one sends requests to same database, and all these requests are both read and write requests. But over time, this becomes performance bottleneck because of the too many requests being handled by only one DB. So what can you do? One way is to break this up and say, no, I'm not going to use one database. I'm going to use a number of databases. You can have a database. Okay, I will draw it. Say we have one database, or rather, let me put it actually still down here. So I'll remove this one. I'll say we have a database that is still responsible for picking and accepting requests from our servers. And I'll call it maybe DB1. It accepts write requests, only write requests. When this database receives these write requests, we can have other databases that would be database 2, database 3, and maybe database 4. Okay, it can be any number of databases according to your needs. So when you have these ones, every time someone writes to database 1, that row is then duplicated or replicated directly to database 2, database 3, and database 4. So we can say that we have only database 1 which accepts write operations. And then database 2, 3, and 4 are only replicated 2. No server sends a write request directly to database 2, 3, and 4. If a server wants to make a read, it can only read from database 2, 3, and 4. So let me annotate this. These 3 are for read operations. If anything is to be written to them, it should only come from database 1 as a result of a replication. So if someone says maybe hi and we save the text hi, we replicate this to database 2 and then database 3 and 4. Then in the event that we need a write operation, not write but read operation, we read from 2, 3, and 4. This kind of setup is called a master slave replication setup. Master slave. Database 1 is the master. Database 2, 3, and 4 are called slaves. Understand that. Also, you might find people calling this active passive setup or active passive replication. The concept is the same. The names should not confuse you. The concepts are very much the same. Why active passive? Because database 1 is the only one which gets actively written to or actively updated by the servers. The servers do not actively update database 2, 3, and 4. Databases 2, 3, and 4 only get updated passively through replication from database 1. When you look at this setup, you might think we have solved everything, but no, we haven't solved everything yet. If you look at this setup, there's still kind of a challenge. And let me explain to you the challenge. If this database 1 goes down, okay, of course, we can easily reconfigure the setup and say, okay, let us make database 2 our new master. We update the database configuration to make database 2 the new master, and then database 3 and 4 become our new slaves. But during that time of updating your master, okay, of upgrading database 2 to master, and 3 and 4 remaining your slaves, there is still some downtime, okay? It takes some time. And of course, if you have an application that requires write operations, okay, you will have something being affected, okay? The experience won't be good during that time. Something else can be done to improve this, and that can be called master to master setup or replication. Let me explain. Instead of having database 1 only, I can have another DB. I'll call it DB0. Come here and say we have a DB, and this DB is called DB0. DB0 is also another master. So we have a master DB, and we have another master DB. Master 1 can accept write operations. Master 2 also accepts write operations. Okay, this makes it much more efficient, okay, and gives us a more reliable setup and high availability. So in the event that DB1 gets an issue, okay, and it cannot receive write operations for one reason or another, maybe the storage is now full or something went wrong and the configuration maybe messed up and it went down, we can simply take all our requests to master DB0. This second master will accept all our operations. And still, we can keep our slaves that when master 2 is also written to, we have all the data in master 2 being replicated to database 2, 3, and 4, which are still slaves. That can still happen, okay? So ideally, when you have a request being sent to master 1 or DB1, you have it also being stored in master 2. Do you know that? And so that, let us say maybe DB1 has 1, 2, 3, and 4 rows. They are replicated to master 2 with 1, 2, 3, and 4 rows. So that when master 1 dies and is kicked out, we have master 2 taking over as the new master. And we can write now the 5th row without downtime, like in the previous setup. In this kind of format or setup or organization of your database architecture, where you have 2 masters or 2 database nodes, whereby any of them can be written to, not only one, is called an active setup or a master setup, whereby you have more than one node which you can read and write to, or read from and write to. So any of these nodes, in fact, in the real world, you can even have more than maybe 10 slaves, depending on what you're doing, okay? You can have maybe more than 2 masters. It all depends on the need and your setup and your business requirements. So I'll remove this and talk about one more thing. In this kind of setup, when you're talking about database replication or data replication, we can have or introduce something. Instead of having probably, let me remove this, then draw using different color. In the event that maybe we have so many requests, okay, we can introduce a load balancer. A load balancer can not only be used, by the way, for HTTP calls, it can also be used at database level. You can load balance requests to your databases, okay? And let's say maybe you have 4 slaves or maybe 10 slaves which are handling read operations. You can set up a load balancer. I'll add it just right here and say maybe LB, okay, for the DB, whereby requests don't hit your database infrastructure directly. They first go to your load balancer. So all the servers send to your load balancer, okay? And then after that, that is when the requests can now go to your database setup. And that load balancer can help you distribute the load or the requests or the read requests efficiently between your databases. I hope you understand this. Like I told you at some point, system design is all about thinking critically and knowing what to apply at what point. But a load balancer can also be put in front of your databases. So don't cram that. And one thing I want to tell you is that system design is also all about identifying single points of failures. If you look at this new setup, this load balancer can also be identified as a single point of failure. You can have another load balancer introduced for you, okay? I'll say LB. This is LB1. Let me try to write it better. Load balancer 1. And this other one is load balancer 2. So load balancer 1 and 2 now work together. This is how it can happen to avoid a single point of failure. In the event that load balancer 1 maybe dies, okay, and they've been working together actively, okay, whereby load balancer 1 sends a heartbeat to load balancer 2 saying, I am alive, I am here, okay. A heartbeat is simply a simple packet sent to another sub or load balancer to tell you that, yeah, I'm just working. So load balancer 1 keeps sending a packet to load balancer 2 to tell you that I'm just okay, I'm okay, nothing's wrong. And servers still send their requests to load balancer 1 from time to time. All requests are going to from server 2, 1 and 3 are going to load balancer 1. And in the event that maybe load balancer 1 goes down, load balancer 2 will identify that, okay, I'm not getting requests anymore. What is going on? I'm not getting the heartbeat from load balancer 1. So it will become the new load balancer that now accepts requests. Okay. All the requests now start going to load balancer 2. This kind of setup in load balancers is called active load balancer setup. You get? Whereby load balancer 1 and load balancer 2 are working together in such a way that one load balancer keeps sending, okay, a packet to the other load balancer saying, I am awake and I'm ready for anything. In the event that this load balancer 1 that is sending packets to this other one goes down, this other load balancer automatically takes up the work of load balancing. It's called an active load balancer setup. Then there's also an active passive in load balancing, whereby you have two load balancers and load balancer 1 is still taking requests from our servers, okay, and it's doing the load balancing very, very efficiently. Then, but this has no heartbeat, okay, notification. There's no way that load balancer 1 is telling load balancer 2, okay, I'm awake. No way, okay. Load balancer 1 just keeps on handling everything, taking the requests, okay, taking the requests. In the event that it goes down, okay, this one is upgraded to the work of load balancer 1, okay. Of course, there's some kind of downtime, takes some time because of that upgrade time, okay, in this active passive mode. But that's how it actually works. So I hope you've understood this. If there's nothing that you've picked, okay, or anything that is confusing you, please let me know in the comment section. Like I said, I'm trying to bring up these concepts step by step without trying to go too complex, but increasing the complexity slowly at a time. That's my goal of this playlist, so that by the end of this playlist, I have gone from something simple to things which are much more complex. In the long run, I want to actually implement these things and show you how you can practically do the load balancing, set up the master slaves, the replications, active, whatever we have all discussed in this playlist. So like, share, subscribe, and complete this playlist to be able to understand everything. So I will be going to the next section to talk about even something more interesting. See you over there. Let's talk about partitioning. It's an important concept that can help you work with scale. And later, I will even go deeper into it. Actually, everything that I'm talking about, I need to go deeper by showing the actual practical implementation beyond just the design on this board. Now, partitioning is a technique that can help you handle scale, and it can help you in a way that instead of having to deal with large data sets, large tables in your complex database, you can divide your data in such a way that out of those large tables or large chunks of data, only particular data sets are selected or are used to query data. Okay, so you query from this subset or this small chunk that you've divided from the larger set, and that alone can help you improve performance. So, like I've said, you have your DB that is really huge. Okay, and I want to show you the several types of partitioning that you can have. So you have your database. So this can represent your database, not database, but database table. And with your table T, you can now divide. Okay, let's say you have maybe this is row 1, row 2, row 3. Okay, and then these other rows down. Then you have your columns. These are columns, and then somewhere, what can I do? Let me label them. This is row 1, row 2, row 3, row 4, and row 5. And then you have column 1, column 2, column 3, and column 4. So what can happen is this. You can divide your table according to the rows. Maybe say maybe rows 1, 2, 3 are my first partition. Okay, and then you also logically separate out row 4 and 5 and maybe onwards. So this way of partitioning by rows can be called horizontal partitioning. Okay, logically separating your data or dividing your data in a single database. And by the way, know that all this is happening in a single DB. Okay, so maybe I can just write it to drive the point home. This is a single DB. Also, you can decide to partition using the columns. So maybe you say, I want to pick row 1 and up to row 2. Of course, this is a basic example. And you can also say, I want another division from row 2 or row 3 up to row 4. So those are a number of partitions, and these are now separate. Okay. Then something else you can do is to have them divided again by, of course, the same idea as maybe rows or columns. But this time, after you divide them, let me get a different color, you pass them to a different server. Okay, so if I have, let me pick a different color, okay, I've got it. You have a number of servers. You have server 1. Okay, so this is server 1, and this is a database server. You have another server here. I'll call it server 2. And then you have another server right here. I'll call it server 3. And again, these are database servers. Okay, these are D servers. So I'll say D dash server. Now, you can have your partitions in each of these separate database servers. So you have a partition here, you have a partition here, you have a partition here. Each of these partitions are called shards, and this technique is called sharding. Okay, so sharding is a technique whereby you divide your database, and those divisions are called shards, and they live on different physical or maybe virtual databases. Okay, but understand that they are on different nodes, different database servers. So when someone talks about partitioning, most cases they're talking about dividing their data by either a column or a row, columns or rows on a single database server. Understand that. Then when people talk about sharding, they're talking about having partitions on different servers. Okay, it's a little complex, and these partitions are called shards. Okay, these shards are identified by what is called a shard key. Okay, a shard key is simply a unique column, for example, like user ID, that is responsible for identifying the starting row, or not the starting row, but for identifying the row where that it identifies where a row lives on a particular shard. Okay, so that shard key simply helps you to identify that this row, where does it belong to? Is it on shard 1, shard 2, shard 3? As simple as that. And that shard is simply a column that you use for identifying where that row lives. As simple as that. So these are things that I am going to go into their practical implementation. So I'm looking forward to going deep into these things as we progress in future. So let's go to the next section where I'm going to talk about something also interesting. Our setup lives in a data center, and let's say you have maybe your data center, okay, and it's called DS, okay, having probably your servers, okay, server 1, server 2, or any number of servers, okay, and you're doing your horizontal scaling. And of course, data center needs a power source, okay. You need that cable that is bringing electricity to your data center. You need also a source of water, okay, very, very necessary for cooling and stuff like that. Okay, so you have electricity, or I can simply say power, and many other resources. Of course, in the event that anything happens, maybe to the water source or to the power source, it could be anything. Okay, this could bring your data center down. The whole point is that your data center can go down, and this has happened several times in the world. Even data centers handled or managed by AWS and actually owned by them have gone down many times. The question is, how do you fix this? So how they fix this is by having what they call other data centers. Okay, so you can have, for example, this whole setup replicated in a different location within the same maybe district. Okay, but still, what if the whole district is maybe main source of the resources takes down all the data centers? That's where now guys like AWS and maybe Azure and Google try to have what they call availability zones and several regions, whereby you have data centers across several regions. You have maybe in Europe, you have maybe in Africa one, you have one in South America, North America, okay, and maybe in Asia, and you spread them across the world. This is another way that you can handle maybe a single point of failure concerning your servers. How do you think traffic is routed to several servers? It is something that you need to think about. How is traffic handled? Imagine maybe you have lots of traffic, okay, and you need to handle that kind of scale. How is it handled between multiple data centers? This happens using something that I talked about in either video 2 or video 3, and that is of course via the internet still, but using DNS. Okay, if you want to understand how DNS works and understand it at a very basic level, please check out the videos in this playlist. Either video 2 or video 1 talks about this. Both of them have timestamps where you can check and see the particular point in time where I talk about the concept. But at DNS level, we can also do load balancing. Okay, so whereby you as a user, you don't know what data center is serving you. In a DNS level, the IPs of these locations, okay, are known logically, whereby maybe your request can go maybe to DS1 or maybe DS, maybe 2, or wherever it is in the world. Just know that, okay, that at DNS level, you can also do load balancing. But there's some small caveat that I want to talk about. On your laptop, if your laptop, again, I repeat, make sure you watch the video about DNS and how it works. Very important. Because what I'm touching right now here was dealt with in that video or that section. So now, let's say maybe you looked for a website, okay, your .com fancy website where you got your important information, okay, but then it goes down because maybe a data center, maybe let me call it DSB, okay, a data center B is down, and your DNS on local machine, okay, has cached the IP address of maybe a server in this particular location. And because this server is down, you can't get help. You get, even if the load balancing at DNS level is now routing traffic away from this data center B to data center A, because this one is down, the load balancing at DNS level routes traffic to A. But because of the IP that you have here cached on your local machine, you're still not getting a request because your computer does not know about this other one yet. So what happens after some time, maybe minutes, hours, okay, depending on the TTL configuration. Okay, again, to understand TTL, please check the videos before this video. So when the TTL, which is time to live configuration, maybe if it was maybe 2 hours or 1 hour, after it expires, okay, when the TTL expires, that is when now you'll be able to see your new content. Okay, not new content, but you'll have your application or your website load again. Why? Because it has expired, and according to the DNS, now traffic is being routed to other data centers and not this data center. And by the way, whatever data center serves your data or serves requests or serves responses to the requests from your servers, it has to serve the same thing. Okay, if a response from maybe data center A was maybe a video for my request, it should be the same video from data center B, data center X, Y, Z, whatever. Okay, whether I have thousands of servers or hundreds of data centers, still the requests have to be served as the user expected, and the responses have to be the same. All right, we're coming to the end of this video. I hope you've learned something very, very important about system design. And yeah, this is how you can handle scale even at DNS level. Like I said, we're going deeper and deeper. Let me now talk about something else in the next section. So this one looks obvious, but sometimes you overlook it, okay? But of course, in your whole setup, it's important to have security. And I think it is something you need to really, really consider. So of course, you can think about it from the whole data center level. Let me draw this as my DS or data center around this whole thing, okay? So into your data center, of course, you need to restrict who is coming in, who's not coming in. You may decide to say, I want everything, okay? Come in, maybe on port 80, the popular TCP port. But even then, you may be very cautious and say, no, I only want HTTPS traffic, which now comes via port 443. Okay, I hope it's 443. If I'm wrong, please let me know. And then you can have maybe your servers deal with port 80 traffic. Okay, because you want to offload the SSL certificate encryption decryption stuff to the load balancer. And then internally, you can only have port 80 so that you don't have that extra step of SSL termination. Then again, if you want to understand all this, I have explained it and touched on it in the previous videos. Then the same thing for your database, okay? You might want to have also safeguards, okay, for the traffic that is going to your database. For example, on MySQL, it could be port, I think 3306, if I'm not mistaken, but it should be a number similar to this or close to this. And you want to be very careful with how you set this up so that in such a way that if someone maybe compromises server 2, okay, they should not be able to make maybe communication or make calls to server 1. They should be stuck within this server 2. If someone went to your database, okay, and compromised it, they should not be able to send requests from your DB to probably server 3. That's kind of how I think of it. And of course, like I tell you, and I've been saying this, system design is about trade-offs. And coming up next in another video, I want to go deep into trade-offs and talk about trade-offs very, very carefully. Because what applies certain times may not apply everywhere. Okay? So think about the business case, think about the challenge you have at hand, and try to think through it. Okay. Sometimes you may not even have to think through it alone. You may need someone else, technical like you, to analyze a problem, discuss it, not one day. Sometimes you may need days, months to understand the problem. And the more you talk about it, the more you think through it, the more you design, the better you get at it, and the better you understand the challenge that you have. And that helps you craft a better solution. All right. So I think this has been an awesome video. There are maybe a few more things I may touch on, but I don't think there are so many. Maybe 2 more sections before we close up this video on scalability. I know we've talked about data replication, talked about master slave and the master setup, but I wanted to touch something again on data and how you can even help yourself scale. Okay, so think about this. What if you didn't go maybe that route of master scaling replication techniques, okay, that I talked about, and you do this from the beginning in your setup of your data, you first denormalize your data, okay? You denormalize it, and after that, you try to ensure that from the beginning, you avoid joins, okay, in your queries. You avoid joins. And if your type of data and setup makes sense to you, you can even go ahead and use maybe a NoSQL database or even a SQL database, okay? But the goal is to have a type of database that can horizontally scale better. And NoSQL databases have this talk around them for being so good at scaling, okay? But the goal is start by denormalizing your data and avoid joins. Once you have these, okay, do your joins in your application code. Join in your code, in your application code. So the joins are not happening at database level, but they are happening at code level. Okay, have this in your mind. By doing this, you'll have a faster experience. Okay, and some of these things cannot be taught or understood until you do them. And my plan is to illustrate how the things can actually be done. And of course, this is not like holy grail and perfect, like I've told you. Always think about trade-offs in system design. In the next section, I want to talk about something that can help this even get better. Okay, this is not just the whole thing, but something that can help this get better. Because even with this, you still need it. I have already talked about catching in this playlist, but there's something more to it that I want to put across in this section. Now, like, catching simply means storing your data in your memory, okay? RAM to be precise. Now, you can catch your database queries. That is something that probably you know and you have been doing. You can catch your DB queries. But one challenge with this is that when your queries get complex, it becomes difficult to deal with the expiration of a complex query. For example, in case you have maybe this as your table, and then of course your table has a number of rows and you have a number of columns. When one particular cell is maybe deleted, not deleted, but maybe updated, okay, or it changes, it becomes tricky, okay? And of course, you can do it, but it's just more complex. You'd have to make sure you delete all cached data that involve this particular cell alone. I hope you get it. There is something which could be better approach when you're catching. Let's look at it from our application level. Instead of catching your DB query, instead what you do is to have your data represented as an object in your application code. So you fetch your data from your DB to your application code, okay? And then you have your application, okay? Let us say your class. That is a representation or a mirror of your data from your database. And this class probably even has all functions or methods that are responsible for acting on this data. And maybe your data is maybe stored in a property called maybe data from DB or simply just data. And it could be an array having your data, okay? Whatever it is, okay? I don't want to go into the specifics of how you'll maybe represent it in your application code. But the whole idea is that you have a class representing your data from your database. And then you have this data as an object or an instance that you now store. So from your app, of course, you have your class, and it's from this class that you have your object or instance. And then it's this instance that is now stored in memory or in your cache or your RAM, okay, using something like Redis, okay? And with this, trust me, it gives you a better experience when you have maybe complex queries and you have to maybe handle deletions or update your cache when a particular cell has been maybe updated or written to, something like that. This makes it much, much better, whereby in case maybe something happened, you can simply delete that object from your memory or from your cache. And it's much, much easier or better experience, even for you as a developer, okay, than having to deal with it. Like I say, some of the things are much better understood when you deal with them. Try to handle caching of your database query when you delete a particular cell or update a particular cell in your database, and your cache or your queries that have dealt with that cell have to be updated, okay? Versus catching an object that represents your results or your database queries or something like of the sort. It's much, much easier. So the whole idea is to catch objects, okay, instead of catching DB queries directly. But again, like I tell you, it's all about trade-offs. If you have a use case or a situation whereby catching a DB query is better than catching a object, please go with the DB query. It's all about trade-offs and applying things to particular situations. So just always make sure you understand the challenge at hand. I hope this gives you a little bit of more understanding on what is possible when you're designing systems. So yeah, that's it. It makes everything much easier when you want to handle changes to your data. And yeah, it makes the whole operation, even in your code, much faster, cleaner, and better for you. Like I said, try it out and you'll see. Let me talk about asynchronism. So how can this help? Think about this. If you have data that is maybe so large and you want to use it maybe to serve and maybe create HTML pages, but it's too much, okay? What you can do is prepare this data ahead of time, okay? Prepare it ahead of time, okay? Prepare ahead of time. And by preparing this data ahead of time, maybe you fetch the data from the database and then create, for example, HTML pages early, so that when the user now wants this data, you serve it to them, maybe the HTML page. You fetch it ahead of time, create the HTML page, and then when the user wants it, simply give it to them, instead of them having to wait for the process of compiling that your data, preparing this data, and then generating the HTML pages. That would be a whole lot challenge, okay? So doing things ahead of time can help you in handling scale. Then the other technique is, what if you do not know what the user wants and it is so dynamic? That is when you tell the user, okay? So maybe a client has made a request, they want a particular resource, okay? And this client C, of course, does not know that it could potentially take a lot of time, but you know, okay? So what you do is this. That client sends their request, okay? And then you simply inform them and tell them, you know what? Your request is being processed, okay? It will be ready, and we shall maybe notify you when it's ready. And then under the hood on your server, okay, you offload that task, okay, to maybe a job queue or something else, okay? I do not get into the details of it, but you offload it to another tool that processes it, okay, and is done with it at a certain point in time. When it's done, then your tool can tell your server, okay, I am now ready with this. And then you can now update the client and say, whatever you needed is now ready for you to consume, or here is what you wanted. This is the whole process of what they call asynchronism, or having async tasks. That certain things, or certain requests, or certain operations can take long. So because they can take long, tell the user this is going to take some time, or they can be done in background, okay? And they shouldn't block other operations, okay? The goal is that whatever is going to take long should not block other operations. But that long thing that is going to take time, whenever it is done, we can notify whoever is needing it that, okay, this took a long time, but now is ready for you. That's the whole goal of this. Whatever takes long should not block other requests, but can be handled separately and then given or served when ready. This is the last piece of scalability I'm talking about in this video, but the other things that I want to build up on in the next video. So thank you for learning, and in the next video, look up for something even more deeper. Like I told you, I'm going to be building on this step by step. See you over there.